NASA's James Webb Space Telescope has found a planet that should not exist. Not in the sense that it is unusual or rare or surprising in the way that astronomical discoveries are often described as surprising to make them sound more exciting than they are, in the literal sense. This planet, as observed and measured by Webb, breaks the physical laws that govern how planets form, how they maintain their structure, how they orbit their stars, and how they behave under the conditions they are currently sitting in. Every model we have built over decades of planetary science, every equation we use to predict what planets can and cannot do, says this object should not be there, and yet the data from the most precise space observatory ever built says it is. That is not a headline written to get your attention. That is the actual situation that planetary scientists and astrophysicists are now sitting with, looking at Webb data and trying to figure out which part of our understanding of physics needs to be revised to account for what this telescope has shown them. Let us start at the beginning so that everything that follows makes sense. Planet formation is not a random process. It follows rules that are well understood, well tested, and supported by centuries of mathematics and decades of direct observation. When a star forms from a collapsing cloud of gas and dust, the leftover material that does not fall into the star forms a rotating disk around it. That disk is called a protoplanetary disk. Inside that disk, particles of dust and ice begin sticking together. Small clumps attract more material through gravity. Over hundreds of thousands and then millions of years, those clumps grow into planetesimals, then into protoplanets, then into full planets. The size of the planet that forms depends on how much material is available in its region of the disk, how far it is from the star, what temperature that region of the disk is, and how long the disk lasts before the star's radiation and stellar winds blow it away. These rules produce predictable outcomes. Rocky planets form close to the star, where it is too hot for ice to exist, and only rock and metal can condense. Gas giants form further out, where temperatures are cold enough for ice to exist, and where there's enough mass available to accumulate the enormous envelopes of hydrogen and helium that define them. There is a boundary in protoplanetary disks, called the frost line or snow line beyond which water freezes. And the position of that boundary relative to a star is one of the key factors controlling what kind of planet forms where. This framework, called the core accretion model, is the dominant theory of planet formation. It is not perfect, it has gaps and edge cases, but it successfully explains the architecture of our own solar system and the general patterns seen in thousands of exoplanet systems discovered over the past 3 decades. What James Webb has now found is a planet that does not fit this framework in multiple simultaneous ways. Not one anomaly, not one measurement that is slightly outside the expected range. Multiple fundamental could survive. Gravitational interactions with the star, with other bodies in the system, and with the star's own tidal forces should have either pulled the planet into the star or flung it out of the system long ago. When you run the simulations backward from the current observed orbit, using the best gravitational models we have, the math does not work. The planet should not be where it is given how long the system has existed. Temperatures Webb has measured for that atmosphere. Other molecules that should be abundant, given the planet's mass and composition, are effectively absent. The chemical fingerprint of this atmosphere does not match any planetary atmosphere in our catalog, does not match any atmospheric model for a planet of this type, and in several specific respects defies the basic chemistry of what molecules can exist together under the conditions that are clearly present. Chemists and atmospheric scientists looking at this data are not saying the measurements are wrong. The instruments on Webb are calibrated to a level of precision that makes systematic error at this scale essentially impossible. They are saying the chemistry they are seeing should not be physically possible, and they do not currently have an explanation for why it is happening. Combination of materials. It is too low to be rock and metal. It is too high to be a hydrogen and helium gas giant. It sits in a range that planetary scientists call the radius gap, a region where almost no planets exist because the physics of planet formation and atmospheric evolution strongly push planets to one side or the other of this gap. Not only is this planet sitting in the radius gap, but its specific density value within that gap does not match any theoretical model for what a instruments and different physical principles, and all four of them pointing to an object that the laws of planetary physics, as we currently understand them, say cannot exist. The scientists working with this data have been public about their confusion, which is itself notable. Scientists are generally cautious about claiming something breaks the laws of physics, because those are extraordinarily strong words with enormous implications. When physicists and astronomers use language like that openly, in papers and interviews and conference presentations, it means they have exhausted the normal explanations. It means they have checked the data multiple times. It means they have looked for instrument error, for calibration issues, for measurement artifacts, for alternative interpretations of the same numbers. And none of those alternatives have resolved the problem. When you hear a planetary scientist say, "This should not be possible," what they are actually saying is, "We have done everything we know how to do, and we cannot make this fit." So what does it actually mean when something breaks the laws of physics? It is important to be precise here because the T phrase can sound more dramatic than it should or less significant than it is, depending on how it is understood. The laws of physics are not absolute eternal truths handed down from somewhere outside the universe. They are our best current models of how the universe behaves, built from observation, tested against prediction, refined over time. When something appears to break those laws, it means one of a small number of things. Either the measurement is wrong, which in this case has been ruled out to the extent that Webb's precision allows, or the laws are being applied outside their range of validity, meaning the physics we use works perfectly well under normal conditions. But this situation involves conditions extreme or unusual enough that our equations break down in ways we did not anticipate, or the laws themselves are incomplete, meaning there is some aspect of physical reality that our current models do not account for, and this planet is showing us the edge of our knowledge. The third option is the one that has the scientific community most energized, because it happens to align with problems that already exist in physics independent of this discovery. Planetary science is not the only field that has been bumping up against the limits of existing models. Cosmology has the Hubble tension, a persistent and now statistically significant disagreement between different methods of measuring how fast the universe is expanding. Particle physics has anomalies in the behavior of certain subatomic particles that do not fit the standard model. General relativity and quantum mechanics remain fundamentally incompatible at the mathematical level, despite both being extraordinarily well tested in their respective domains. Physics is not a closed book. It is an ongoing project with known gaps in it, and every time an observation appears that does not fit existing models, one of the possibilities that has to be taken seriously is that the observation is revealing one of those gaps. This planet could be doing exactly that. It could be sitting in a region of parameter space, a combination of size, mass, orbit, age, and atmospheric composition that, your models never had to account for before because we had never seen anything like it. And in that region, our models fail not because, they are wrong about everything, but because they were built from observations that never included anything this unusual. The equations we use for planetary interiors were calibrated against planets we already knew. The atmospheric chemistry models were built-in to match atmospheres we had already seen. When something genuinely new appears, something outside the range of what the models were built on, it is not surprising that the models fail. What matters is what we learn from the failure. The James Webb Space Telescope is revealing things about the universe that previous instruments literally could not see. Its infrared sensitivity, its spectroscopic resolution, its ability to look at distant and faint objects with unprecedented clarity. That means that for the first time, we are able to make precise measurements of objects that we previously could only detect at all. When you go from barely detecting something to measuring it in detail, you sometimes find that the detailed picture is completely different from what you assumed it would be. That is not a failure of science. That is science working exactly as it is supposed to work. He universe does not owe us the courtesy of fitting our models. Our models owe us the honesty of breaking when reality disagrees with them. What happens next with this discovery will be worth watching closely. Other telescopes will be pointed at this planet to attempt independent verification of Webb's measurements. Theorists are already working on models that might explain one or more of the anomalous characteristics, looking for combinations of physics that could produce what Webb is seeing, even if those combinations are unusual or previously unconsidered. Papers will appear in peer-reviewed journals where other scientists in the field will scrutinize the data, the analysis, and the conclusions with the full force of scientific criticism. That process is slow and sometimes contentious, and that is exactly how it should be, because the claim being made here is significant enough to require that level of scrutiny. But the data is the data. Webb has been operating long enough and has been validated thoroughly enough that its measurements are trusted by the scientific community in a way that is not easily dismissed. When Webb says, this planet is where it is, the size it is, the mass it is, and has the atmosphere it has, those are not preliminary guesses. They are precise measurements made by the finest space observatory humanity has ever built, and they have been checked by teams of scientists who wanted very badly to find a conventional explanation and could not. A planet that should not exist, in an orbit it should not be able to maintain, with an atmosphere that should not be chemically possible, with a density that matches no known material, found by a telescope that does not make mistakes at this level. This is what the James Webb Space Telescope has handed planetary science. The field is not going to look the same on the other side of figuring out what it means. Every law of physics we use to understand planets was built from planets we had seen before. We are now looking at something we have never seen before. The laws are going to have to catch up.